Our next topic for this course is on failure. Okay, in this topic, we are going to look at three different types of failure, which are fracture, the first one, and then fatigue, and the third one is creep. For each type of these failures, we will be discussing on the mechanism, how it occurs, testing techniques, okay, how we can test the type of failures, and finally the method by which failures can be controlled. Everybody, especially material engineers, they don't want any failure of materials to occur. Okay, because it will cost them a lot, including it will possibly threatening humans' life. But sometimes incident happen and failure of materials may be due to the improper material selections or improper materials processing, improper design of the components, and improper use or misuse of the materials. So therefore, material engineers always need to anticipate or to predict, okay, and plan for possible failure in order to prevent it from occurring and avoid any incident. The first type of failure that we will be discussing is fracture. Fracture can be defined as the separation of a material into two or more, okay, pieces. Okay, the material break into two or more pieces due to the two potential reasons. Okay, there can be two possible reason why materials break into or fracture into two or more parts. Okay, the first one is stress. Okay, the stress can be either tensile stress, compressive shear, or torsional stress. Okay, this one we have discussed on the previous chapter. And the second reason material is separate into pieces is because of the low temperature. Okay, which means low temperature relative to the melting point of the material. Okay, for engineering materials, there are two fracture modes are possible. Okay, there are two types of fracture, ductile and brittle. Okay, the classification of fracture, either ductile or brittle, is based on the material itself. Either the material will experience plastic deformation or no plastic deformation. Any fracture process involves two steps. Okay, the first one is crack formation and then followed with crack propagation. Okay, when we apply stress into a material, when the stress applied is too consistent throughout the time, it will crack, and then it will forming a crack, and then the crack will propagate. Okay, um, and this step of crack propagation will determine either the fracture will form the ductile fracture or brittle fracture. The image here shows schematic representations for three fracture profiles. Okay, either highly ductile fracture, moderately ductile fracture, and brittle fracture. First, a highly ductile fracture is happen for extremely soft material. For example, pure gold and lead at room temperature, and also happen to polymer and glasses at high temperature. If you look at the area here, okay, the highly ductile materials neck down to a point fracture producing 100% area reduction. Okay, if you compare surface area before the fracture and after the fracture occurs, it reduced by almost 100% from its original surface area. So we can say the area percentage of area reduction is large. Okay, and the second image here is the moderately ductile fracture, which is the most common type of fracture. It forms only a moderate amount of necking. Okay, if you can see here, image here, the neck here is moderate amount. Okay, and this type of fracture is normally happen to metals. And the fracture process for moderately ductile fracture occurs in several stages, and we will look into details of each of the steps in the next slide. And the third image here is for brittle fracture, okay, where we can see the percentage of area reduction is small as compared to the original surface area of the original material. Okay, after the fracture, there is a very small little change in area reduction. Okay, and this kind of brittle fracture normally happen for materials such as ceramic and cold metals, metal at low temperature. If we compare between these highly and moderately ductile fractures, they always occurs with warning. With warning. Okay, for highly ductile and moderate ductile fracture, they always occur with warning. Okay, while the brittle fracture, it occurs without warning. Okay, so we can say that ductile fracture is always preferred, okay, by the engineers rather than brittle fracture, because it allows engineer to take preventive measures. This slide will describe in details the process or the steps involved in cup and cone fracture. Okay, a cup and cone fracture is a type of failure observed in ductile metals or ductile materials that are subjected to an excessive tensile stress. Okay, it is actually the separation of a body into two separate pieces. Okay, separation of metals or materials into two separate pieces as we apply excessive tensile stress. Okay, we get this name of cup and cone fracture because of the resulting shapes after the metal or materials broken into pieces. If you look at this last image here, one part forming the cup shape and another part forming the cone shape. Okay, if you look at the details of the process, when we apply the metal or the material to a tensile stress, okay, we apply the stress here, and as the tensile stress in the metal approaches its yield strength, a small portion of the metal's cross-section area decreases in a process that we call it as necking. Okay, we apply stress to this metal, it will stress out the metals and forming necking. Okay, so it will reduce in cross-sectional area ataupun cross area. Okay, as the load continues to increase, okay, small cavities will form, okay, at the neck portion of the material. Okay, increase the tensile strength ataupun we increase the tensile stress, cavity starts to form. Okay, and any further increases in the load will cause the cavities to grow in size. Okay, so it eventually coalesce or merge. Okay, the cavities will coalesce or merge to form an elliptical crack. Okay, and this we call it as elliptical crack, which is perpendicular or 90 degree to the stress direction. Okay, we apply stress this direction, and the coalescence of cracks or coalescence cavities will form 90 degree from the stress applied. Okay, finally fracture occurs. Okay, around the neck. Okay, and this we call it as a shear deformation at an angle about 45 degree with the area or with the direction of tensile stress that we apply. We apply tensile stress here, and we can see the forming of shear stress. Okay, fracture which is 95 or 49 degree from the stress applied, and we call it as shear stress. And eventually the material fails, okay, break into two pieces, and the fracture ends of the material forming the cup and cone shape. If we examine the fracture under the electron microscope, we can clearly see the interior surface of the fractured materials forming fibrous, irregular, and shear effect, which indicate plastic deformation of the material. So these images here is scanning electron microscopy, ataupun we call it as SEM. Okay, SEM is scanning electron microscope image of tire cord wire. Okay, tire cord wire is a wire in the tire and that experience ductile fracture after being applied with tensile stress. Okay, this is what happened to the wire. In the next few slides, we are going to look at the second type of fracture, which is brittle fracture. Brittle fracture takes place by a rapid crack propagation, and because of the fast propagation, there is no considerable or there is no clear plastic deformation can be observed. Okay, we cannot see the plastic deformation, or there is no plastic deformation formed. Okay, the crack propagations occur nearly perpendicular to the direction of applied stress. Okay, if we apply stress in this direction, the crack will propagate 90 degree to the direction of the applied stress, and the shape that form after the fracture is almost flat shape. Okay, so that's why we say there is no plastic deformation for brittle fracture. Brittle fracture can occur in two ways. The first one is transgranular fracture. This type of fracture happens because the cracks pass through the grains. Okay, if we take a piece of metal under electron microscope or SEM, the surface of metal is actually forming from 1,000 pieces of grains. Okay, if you look at this image, there are several pieces of grains, okay, and they combine together to form the metal. Okay, if we look at this under the microscope, SEM image, we can see the transgranular fracture occurs due to the crack that propagate through the grains. Okay, it passed through the grain. Okay, we have several grains here, and the crack propagate through it. Okay, and the fracture, the surface of the fracture, it will form faceted texture ataupun tekstur yang bermuka. Okay, as you can see from this image, SEM image here. Okay, we can see the texture becomes faceted texture. Okay, this kind of faceted texture form because of the orientation of the crack is different. Okay, orientation of the crack here is different from one grain to another grain. The second type of brittle fracture is intergranular fracture. Okay, this fracture occurs as the crack propagate along grain boundaries. Okay, if we look at this image here, the crack propagate along the grain boundaries. It follows the boundaries of the grain. Okay, it does not like transgranular fracture, it across the grain, but this one, it occurs along the grain boundaries, and this will make the grain boundaries weaken, and the surface of materials that experience intergranular fracture will look shiny and smooth surface, as shown in this SEM image here. There are some cases where ductile materials experience brittle fracture. Okay, due to this, material scientists or engineers need to have a better understanding on the mechanism of fracture. And the research on materials fracture have been extensively studied, and it comes to the field of fracture mechanics. So from this fracture mechanics knowledge, it allows engineers or material scientists to quantify the relationship between material properties, stress level, presence of crack producing flaws, and crack propagation. So from the relationship between material properties and crack propagation, relationship between stress level and crack propagation, and flaws, relationship between flaws and crack propagation. So they will allow them to predict and prevent structural failures. The first mechanics of fracture that we are going to look at is stress concentration. We are going to measure, or we are going to quantify how much stress concentration contributes to the fracture of materials. The measure fracture strength is influenced by the presence of microcrack. These microcracks exist under normal conditions at the surface of a material or within the interior body of a material. So microcracks that exist can be either exist on the surface or within the material of the body. If we apply stress to the material that has these microcracks, the stress may be amplified, or the stress may be concentrated. So that's why we call it as stress concentration. And these microcracks is also known as stress riser. Okay, it amplified, or it concentrated the stress, okay, from the crack exist. We can explain the concentrated or amplified stress or stress concentration by looking at this image. Okay, this is our material, which is metal, with applied tensile stress. Okay, we apply stress, okay, in this direction. Okay, labeled as sigma naught. Okay, sigma naught. We can visualize the crack, okay, the micro crack, as I mentioned before, as similar to the elliptical hole. Okay, imagine that we have crack occurs in the interior body of the material. Okay, and this hole is perpendicular to the applied stress. Okay, 90 degree to the applied stress. Okay, and the maximum stress, or sigma m, occurs at the crack tip if we can enlarge this elliptical hole. Okay, so this is our enlarged image of elliptical hole. Okay, we can calculate the maximum stress of sigma m, which that maximum stress occurs at this area, at the crack tip. Okay, we call this as crack tip, at the edge of the crack. And we can measure how much stress being applied, extra stress being applied from the presence of this micro crack using Griffith crack. So this is the formula: sigma m, which is maximum stress, equal to 2 multiplied with the sigma naught, which is the applied stress. Okay, A is the area of this elliptical hole, divide with the rho t. Okay, rho t is the distance of this crack tip. Okay, square root of this, and this is also equal to the stress concentration factor Kt multiplied with the sigma naught, which is the applied stress. As mentioned in the first video, fracture occurs in 2 steps. Okay, the first one is crack formation, followed with crack propagation, or propagation, we can call it as a spread of the crack. Crack propagation step is determined from the sharpness of the crack tip. Okay, look at these 2 images. This is very sharp tip, and this is blunt tip. Okay, a brittle material will have crack with a sharp pointed tip. Okay, this is the example of tip for a brittle material, and therefore because of this sharp pointed tip, the radius is small. Okay, the radius we use symbol A as shown in the previous Griffith crack formula. Okay, this kind of crack produces a large increase or high stress concentration at the crack tip. Okay, with this sharp tip, it will produce high stress concentration. In order to reduce the stress concentration, okay, we can drill a hole. Okay, drill a hole at the end of the crack, and from this we can make the radius increase. We can increase the radius of this tip, and that means we make the tip blunt ataupun tumpul. Kita tumpulkan tip ni, so that the radius will increase, the A value increase, so the concentration of the stress is reduced.
When you talk about crack, okay, so you must bear in mind the crack or the starting failure, okay, of your material. We start at one point lah. For example, this is your material, okay, so it must have something or somewhere, okay, that start up your crack. Okay, so usually like this lah. And then this crack, okay, when you zoom in, okay, it will looks like a sharp tip. Okay, so this tip here, okay, is very dangerous lah. Okay, lebih kurang lah. Okay, why? Because this tip, okay, can propagate the crack. Okay, that's why in your previous slide, okay, if you want to stop the crack, okay, so you must blunt this tip, tumpulkan tip ni, so that the crack won't propagate. Okay, so in order for you to design a material, okay, so you have know, okay, when does your crack propagate. So you, as a material chemist, you must know, okay, how or when, okay, your crack propagate. Okay. Okay, so as common sense, okay, crack will propagate or must propagate if its stress value above ataupun lagi bigger lah, its critical stress. Kan? So bila lagi besar, so it means that your materials cannot withhold that stress, then your material will fail, and due to what? Due to the formation of the crack. Okay, so this is the crack growth conditions equations. So this is the K. If the K, okay, above its critical value, so it means that your crack can grow. Okay, so with these equations, okay, so you can see lah. Okay, it's either you design your materials, okay, upon the stress value. So it means that you have a stress value. So in order for your materials to avoid the crack or to fail, so you must design your stress value lower than this value. Okay, or okay, you want to fix the stress. Maksudnya stress tu you tak nak ubah-ubah. Okay, maksudnya your samples tu must withstand this amount of stress. For example, kat sini berat lah. Okay, tinggi lah stress dia, berat. So you tak nak ubah the stress value ni. Okay, so what you must do, okay, so you just twist the equations, so you find the area, maksudnya the optimum area for this particular stress, okay, stress yang you tak nak ubah tu, stress tu you memang kena guna that amount of stress, okay, so you play around or you design, okay, your materials depending on the area, maksudnya area ni lah, maybe dia lagi tebal ke, or dia lagi nipis ke, or dia lagi besar ke, okay, macam tu, alright. For example, here you want to design an aircraft wing. Okay, so aircraft ni punya wing lah. Okay, macam pisau. Tak apalah, you imagine lah, aircraft wing. Okay, so it state that this material has this value of K. Okay, and then you have two design to consider. So it means that the materials are the same. Cuma yang beza dia adalah design dia yang berbeza. Okay, so that means the A value will be different. Okay, nampak? Okay, so for design A, with this A value, okay, 9 millimeter, okay, and it stated here this design fail, okay, at this 112 megapascal stress. Maksudnya at 112, okay, with this A value, okay, your apa ni, wings fail. So what about design B? Kan? So how do you look at these situations is, okay, you know that it is the same material, kan, sebab dia kata they use same material, so same material as A, so it means that they have value of Y and KC will be the same. Okay, so kalau you masukkan dalam here, okay, so Y and KC are the same, so it means that the stress value, and then you times with square root pi A will equals to Y, will equals to K over Y. And this K over Y for design A and design B are the same. Why? Because there are same materials. So that's why you can put it like this lah, okay? You can write it like this because K over Y for design A and design B are the same. So you tak perlu pun cari what is the value for this one, ataupun you tak perlu pun cari ni value dia apa, sama dengan apa ni, you tak perlu cari because K and Y value are the same. So you just samakan saja. Okay, so in this case for this design A, you know the stress, okay, at 112 megapascals it will fail, okay, and then the A value is 9 millimeter, and then for design B you need to know what is the stress value. So when you are using 4 millimeter A ni, and then you calculate and you get the stress value for the B is 168 megapascals. So then you know when for an aircraft wing, okay, when you use this A value, okay, your stress, you have a higher stress. So it means that your material can withstand more stress, okay, if it is shorter A value.
When the design material is ready to be used, okay, there is always some element of uncertainty, okay, regarding the stress that it will receive throughout its application. Okay, so meaning that engineers, when they design, when they make new materials, they will do all the testing. But even though all the testing have been conducted, there some element of uncertainty, we don't know what they are, might be occur to the material that has been designed based on the stress that have been applied to the material. Therefore, with that, the design allowance, okay, must be enforced. Okay, the design, how the design the design of material is made. Okay, there is some certain design allowance must be enforced or must be followed to ensure the avoidance of catastrophic failures. Okay, these catastrophic failures might result in personal harm or economic loss or even life-threatening to human. Okay, there are two different design allowance. Okay, maybe can be followed by the engineers or the material designer. Okay, one is design stress or sigma D, or another one is safe stress, sigma W. Either one. Okay, these are the formula, but don't worry, this formula you don't have to memorize. Just to note that these two principles, either one of these must be followed in order to do the design allowance. Next, we are going to look at the impact fracture testing. Okay, the type or the different types of tests that can be used to determine the fracture characteristics of materials. Either the material design will undergo ductile or brittle fracture. Okay, this is important to be conducted because some of ductile material, when it being designed, it should behave as it should show the ductile fracture, but somehow this kind of ductile material can also undergo brittle fracture. Okay, that shows no or very little plastic deformation. So there are two standard fracture tests that are normally conducted, which we call it as Charpy V notch or CVN and IZOT.